Welcome to Chapter 5, Text and Characters. Every value so far has been a number, but programs also show letters, read files, and print messages. So this is the puzzle. When you press the key, the computer stores the number 65, the exact same bits that mean the quantity 65 when you are counting. Nothing inside the byte tells you which one is meant. In this chapter, we build the agreement that decides, starting from ASCII and ending with Unicode. Press the key and the computer stores the number 65. That is the exact same bit pattern that means the quantity 65 when you are counting. Nothing inside the byte tells you which one is meant. The only difference is an agreement about what the bits represent. We call that agreement a character encoding, and this chapter builds it up from ASCII all the way to Unicode. Let us look at the plan for this video. It has 4 parts. First, ASCII, the 7-bit standard that maps 128 characters to numbers, and the deliberate structure hidden inside its table. Second, beyond ASCII. What happened when the world used the 8th-bit code pages, Latin 1, and the garbled text called Mojibake? Third, Unicode. One scheme that gives a single number to every character in every writing system, organized into code points and planes. And fourth, UTF-8, how an abstract code point becomes actual bytes, built 1 byte at a time. Let us start with ASCII, the standard that became the dominant early way to store computer text. Computers store bits, and bits encode numbers. But to show text, somewhere there must be a table that says this number means this character. Without such a table, the byte hex 48 is only the number 72. It could mean anything. With the table, it means the letter H. The early question was whose table. Every manufacturer had its own. IBM used a code called ASCII. Teletypes used BOTA. So a file written on one machine turned to garbage on another. In 1963, ASCII settled on one shared table. ASCII uses 7 bits. 2 to the power 7 is 128 slots, and that was just enough for English. 26 uppercase letters, A through Z, and 26 lowercase, A through Z. 10 digits, 0 through 9. 32 punctuation marks plus the space. And 33 control codes that print nothing at all. Add those up and you get 128 characters. They fit in 7 bits, and in practice they are stored in a full 8-bit byte with the top bit set to 0. This picture lays the ASCII letters and digits out in bands. Look at the top band first, the uppercase letters. They run in one unbroken block. The letter A is code 65, and each letter after it counts up by 1, all the way to the letter Z at code 90. Because the letters are contiguous, the letter at position N after A is just 65 plus N. Now the middle band, the lowercase letters. They form their own unbroken block. The letter is code 97, counting up to the letter Z at code 122. Compare the 2 bands and something jumps out. Each lowercase letter sits exactly 32 codes above its uppercase twin. A is 65 and A is 97. The gap is 32 every time. That constant gap is not an accident, and we will use it in a moment. Finally, the digits band. The digit characters run from the character 0 at code 48 up to the character 9 at code 57. This is the classic trap. The character 0 is not the number 0, it is code 48. So to turn a digit character into the number it shows, you subtract 48. The character 7 is code 55, and 55 minus 48 gives 7. The codes from 32 through 126 are the printable characters, the space plus 94 visible symbols. Everything else is a control character, an instruction to the device, not a shape to draw. Code 0 is null, used in the C language to mark the end of a string. Code 9 is the horizontal tab. Code 10 is line feed, which is the new line on Unix and Mac OS. Code 13 is carriage return, and Windows writes a new line as carriage return followed by line feed. Code 127 is delete. These print nothing, but they shape how text is laid out. Let us read the byte 01000001 as an ASCII code. The method is the same weighted sum you already know. The bit worth 64 is a 1, so it contributes 64, shown in blue for its place value and teal for the running total. The bit worth 1 is also a 1, contributing 1. The other 6 bits are 0 and add nothing. 64 plus 1 is 65, the committed code in teal. Look up 65 in the table, and it is the letter A that is how a byte becomes a character. This is the reason that constant gap of 32 exists. The figure lines up the 2 bytes. Uppercase A is 0100, 0001, which is 65. Lowercase is 0110, 0001, which is 97. Read them bit by bit, and 7 of the 8 bits are exactly the same. Only one position is different, and that position is bit 5. The differing bit is drawn in amber. It is bit 5, and bit 5 is worth 32. For the letters A to Z and A to Z, that single bit is the whole difference between the two cases. Set bit 5, and such an uppercase letter becomes lowercase. Clear bit 5, and such a lowercase letter becomes uppercase. On any other character, changing bit 5 just gives an unrelated result. The designers place the alphabet so that case is 1 bit, which is why letter comparisons and case changes are so cheap on a computer. Let us change case with arithmetic. Start with A, the code 65 in teal, with its bits 0100, 0001 in blue. Now set bit 5 by adding its value, 32, drawn in amber because it is the 1 bit we are changing. 65 plus 32 is 97. 97 is the letter A, 0110, 0001, committed in teal. Adding 32 forced the letter to lowercase, and subtracting 32 would force it back. ASCII covers English and almost nothing else. Now we watch the world try to fill the rest of the byte. ASCII only uses 7 bits, so codes 0 through 127 are well defined. But a byte holds 8 bits, and 8 bits reach 255. That leaves a whole second half, codes 128 through 255, sitting empty. Every vendor and every country filled that empty half with whatever characters they needed. The result is called extended ASCII. It is not one standard. It is many incompatible ones. They all agree on the lower half, but each fills the upper half differently. Each of those upper half mappings has a name, a code page. A code page is one specific table from byte values to characters. Most code pages keep ASCII in the lower half, and the upper half is chosen for a particular language or region. IBM shipped code page 437 on the first PC Microsoft added Windows 1252 for Western Europe and Windows 1251 for Cyrillic. The trouble is that the byte hex E9 is the accented E in Latin 1, a Greek letter in code page 437, and a Cyrillic letter in code pay 1251. Same bits, different character. The most important of these pages is Latin 1, formerly ISO 8859-1. It extends ASCII with 96 printable characters for Western European languages, accented vowels like the E with an acute accent, the N with a tilde, the German sharp S, and signs like the pound sterling and the copyright mark. It covered French, German, Spanish, and their neighbors, and it became the default encoding of the early web. That mattered later, because the first 256 characters of Latin 1 were adopted unchanged as the first 256 characters of Unicode. When software decodes bytes with the wrong code page, the text comes out garbled. That garbling has a name borrowed from Japanese, Mojibake. It is not random noise. Each byte still maps to some character, just the wrong one, so the damage is consistent and even reversible. Take the German word for size, spelled G, R, O with 2 dots, sharp S. E-encoded in Latin 1, it is the bytes hex 47, 72, F6, DF, 65. Hand those exact bytes to a Cyrillic code page and the non-ASCII bytes turn into the wrong characters, so the word turns into nonsense. The bytes were never corrupted, only the interpretation was wrong. This is why a file needs to say which encoding it uses. Code pages prove that 256 slots are too few for the world. The fix was to stop fighting over the byte and build one enormous table instead. Unicode, first published in 1991, gives a unique integer to every character in every writing system. Not just modern scripts, but historic ones like Egyptian hieroglyphs, plus mathematical symbols, musical notation, and yes, emoji. One universal table, and no two characters ever share a number. Unicode also does something code pages never did. It separates two problems. It fixes which character a given number means, and it says nothing yet about which bytes store that number. Identity is one problem, storage is another, and pulling them apart is the whole reason Unicode scales. The number Unicode assigns to a character is called its code point. Code points run from 0 up to just over 1 million, and we write them with a capital U, a plus sign, and the value in hexadecimal. The letter A is U plus 0041, the same 65 as in ASCII. The accented E is U plus 00E9. The Chinese character meaning world is U plus 4E16. The grinning face emoji is U plus 1F600. And by design, the first 128 code points are exactly ASCII, and the first 256 are exactly Latin 1. Plain ASCII text uses these same code points, so it carries over with no change. Unicode organizes that huge range into blocks called planes. There are 17 of them, numbered 0 through 16, and together they start at U plus 0000. They run all the way up to U plus 10, FFFF. Each plane holds 65,536 code points. Most of those planes are still mostly empty, held in reserve for scripts that have not been added yet. The interesting action is concentrated in the very first plane. Plane 0 has a name. The basic multilingual plane, or BMP, it runs from U plus 0000 to U plus FFFF. It holds nearly every character you will meet in ordinary text. Latin letters, Greek, Cyrillic, Arabic, the most common Chinese, Japanese, and Korean characters, Korean Hangul, and thousands of symbols. Rarer CJK characters sit in the supplementary planes. For most everyday text processing, you never leave the BMP. Above the BMP sit the supplementary planes, planes 1 through 16, covering U plus 10000 up to U plus 10FFFF. This is where many emoji live, along with historic scripts, musical symbols, and rare Chinese characters. The grinning face at U plus 1 F600 is in plane 1. The practical point is that these characters need more than 16 bits to hold their number, which shapes how they are stored. One more idea before we store anything. A code point is an abstract number, nothing more. Saying that the character world is U plus 4E16 tells you which character it is, but it does not tell you how that character sits in memory or in a file. Turning the number into real bytes is a separate job, and that job is called encoding. There are a few encodings, but one of them runs the modern world, UTF-8. That is where we go next. UTF-8 is the dominant encoding on the web today. Let us see how it turns a code point into bytes. UTF-8 stores a code point in 1 to 4 bytes, and it spends extra bytes only when it has to. A character in the ASCII range, U plus 0000 through U plus 007F, takes a single byte, and that byte is identical to its old ASCII code. Most Latin, Greek, and Cyrillic letters take 2 bytes. Most of the basic multilingual plane, including the Chinese, Japanese, and Korean characters, takes 3 bytes. And the supplementary characters, like emoji, take 4. Characters with smaller code points take fewer bytes, larger code points take more. That efficiency, plus its ASCII compatibility, is why UTF-8 carries over 98% of the web. The trick of UTF-8 is that the first byte announces its own length. A first byte starting with a 0 is a lone ASCII byte. A first byte starting with 110 begins a 2-byte character. 1110 begins a 3-byte character. And 11110 begins a 4-byte character. Every following byte, called a continuation byte, starts with 10. The little X marks are where the real code point bits go, so you can always tell where a character starts, even if you land in the middle of the stream. Let us encode a real character by hand. The Chinese character meaning world, code point U plus 4E16. First, write the code point in binary. 4E16 in hexadecimal is 16 bits. 0100, 111000, 010110. 16 bits is more than a 2-byte form can carry, but it fits the 3-byte form, which has room for 16 payload bits. So this character will take 3 bytes. Now pour the 16 bits into the 3-byte template. The fixed leading bits are the markers. The X positions, drawn in blue, are the payload, the real data. 16 payload slots, and we have exactly 16 bits to place. They split 4, then 6, then 6. Byte 1 is the marker 1110, followed by 4 payload slots. The first 4 bits of the code point flow into them. Byte 2 is the marker 10, followed by 6 payload slots. The next 6 bits go here. Byte 3 is the marker 10, followed by 6 more slots. The last 6 bits fill them. Nothing is invented. The code point's own bits simply flow into the open slots. Now fill the bytes, 1 per beat. Start from the split. The payload is 0100, 111000010110 grouped 466 all in blue. Byte 1 is the marker 1110, then the first 4 payload bits 0100. That gives 1110, 0100, which is hex E4 committed in teal. Byte 2 is the marker 10, then the next 6 bits 111000. That gives 10, 111000, which is hex B8. Byte 3 is the marker 10, then the last 6 bits 010110. That gives hex 96. Put them together and the character world is hex E4, hex B8, hex 96, 3 bytes for one character. And there it is. One code point became 3 committed bytes. The first byte is hex E4. The second byte is hex B8. The third byte is hex 96. Decoding runs the same steps backward. Read the first bytes leading 1110. Learn that 3 bytes are coming. Strip the marker bits off each byte and glue the payload bits back into the original code point. Encoding and decoding run the same path in opposite directions. This is the property that made UTF-8 win. For any code point from 0 through 127, UTF-8 uses a single byte, and that byte is exactly the old ASCII code. So every plain ASCII file is already a valid UTF-8 file, byte for byte, with no conversion needed. Decades of English text, source code, and configuration files just worked the day UTF-8 arrived. That painless backward compatibility is why it took over the web. Let us gather what this chapter gave you. 4 takeaways. First, ASCII maps 128 characters to 7-bit codes, and its table is deliberately structured. The digits form one block, the uppercase letters another, the lowercase letters another, and for those letters the 2 cases sit just 1 bit apart. Second, once programs use the 8th bit, the world split into dozens of incompatible code pages, and decoding with the wrong page gives Mojibake. The bytes are fine, but the characters are wrong. Third, Unicode assigns one code point to every character across 17 planes, from U plus 0000 to U plus 10 FFFF, and it separates a character's identity from how it is stored. Fourth, UTF-8 encodes a code point in 1 to 4 bytes using leading bit markers, keeps single byte compatibility with ASCII, and now carries the great majority of the web. That is Chapter 5. You can now decode a byte into its character, change case by flipping 1 bit, read code points in U plus notation, and encode a code point into UTF-8 bytes by hand. So far, every chapter has been about representing a single value as faithfully as possible. Chapter 6 changes the goal. Instead of representing data, we ask how to make it smaller. We will meet run-length encoding and Huffman coding, and the important split between lossless compression, which loses nothing, and lossy compression, which trades detail for size. See you there.